So we talked about triangles really extensively, but now we're going to extend the idea and talk about what if you have three sides or more than that. So this is a concept called polygons, and then we're also going to talk about the perimeter of those and the area. So a polygon is just a closed figure in a plane that's determined by at least three straight lines. So our triangles that we dealt with before contain exactly three straight lines. So maybe here's one triangle. That is technically a polygon. But you could also have more sides than that. So maybe I have a figure that looks something like this. This one's got 5 sides, but again, straight lines. And really, instead of doing it like that, I could have done 5 sides like this instead. Okay. So these are all examples of polygons, but they form a closed region. So there's something inside here. So you have what's called an area. You can see how much space this takes up. Now within these polygons though, all of these are called the sides, but the corners where they meet are called the vertices. So all of these are vertices, which is the plural form for it. So the singular form is just one vertex. So where the two sides, or you can also call them edges, meet, these are vertices. So singular, vertex, plural, vertices. And then also, in addition to calling this a side, you'll hear often referred to as an edge as well. So we learned with a triangle there were special types and special names. And we know if it has all 3 sides being exactly the same, the angles were exactly the same too. That was an equilateral triangle. But in general, we call those a regular polygon. So a regular polygon is a polygon where all the sides are the same length and all of those interior angles have exactly the same measure. Now, depending on the number of sides will determine what the name of that particular shape is. So for some of these, not every single number will go through the name, and when I can, I'll draw a nice picture for it, but some of them are a little bit hard to do. So when you have a 3-sided figure, that is going to be a triangle. And that is one I definitely can draw, and I'll try to draw them so it's the regular shape. A 4-sided figure you might think is called a rectangle, but that's actually not the more general name. A 4-sided figure is called a quadrilateral. Okay. So quad is typically used to refer to for 4. But again, the best example we have of that is going to be a rectangle. And we will talk about special types of quadrilaterals as well. 5-sided figure is a pentagon. And these are exactly what I just drew above. So that's 1, 2, 3, 4, 5 sides. A 6-sided figure is a hexagon. And this one I can also draw relatively okay too. So 1, 2, 3, 4, 5, 6. 7-sided figure is a heptagon. Heptagon, a little bit hard to say. That one I am definitely not going to attempt to draw because it's not going to come out pretty. 8-sided figure is an octagon. And this one, hopefully you recognize as our stop sign. So that one I can actually draw a little bit of a figure for. So that's 5, 6, 7, 8. 9-sided figure is a nonagon. And really at this point, I'm not going to try drawing any of these. 10-sided figure is a decagon. 12-sided figure is a dodecagon. And then a 20-sided figure is an icosagon. We're not going to worry about any of the numbers in between because they're not shapes that are seen as frequently. Now, depending on the number of sides, we're actually going to be able to determine what those interior angles add up to. So to kind of just go back up here, we know for a triangle, those 3 angles are going to add up to 180. And we're actually going to see if I have a 4-sided figure, what do those angles add up to? 5-sided figure has 5 angles. What should those angles be? And really, it's all going to be based on those triangles. So how do we know how much the interior angle should add up to? We know that the sum of the interior angles of a triangle must be 180 degrees. So let's try to introduce one more side and look at a quadrilateral. That's a 4-sided figure. Well, really, what I can actually do is just cut this figure from one vertex to the other. And what I've done is I've got one triangle here, and I know that these angles have to add up to 180. And then I've got a second triangle down here. And those angles also need to add up to 180. But those are exactly the 4 angles that are formed by my quadrilateral. So ultimately here, there are 2 triangles. So the measure of the interior angles must be 2 times 180 degrees. So these angles must add up to 360. And again, you can think of your rectangle here, getting ahead of ourselves, but we all have seen rectangles before. All of these angles are 90 degrees. So 90 times 4 gives you exactly 360 degrees. So a 4-sided figure will always add up to 360. If I then bump it up to a 5-sided figure, well, really all I'm going to do is count the number of triangles again. So if I connect these 2, I have 1 triangle here. And then if I connect these 2, I have 2 more. So ultimately there are 3 triangles that form all of the 5 angles of my pentagon. So the angles will add up to 3 times 180, or 540 degrees. Okay? So really there's ultimately going to be a pattern. 4 sides had 2 triangles. I bump up the edge 1 more, I got another triangle. If I had a 6-sided figure, there would be 4 triangles. 7-sided figure would be 5. So in general, the sum of the measures of the interior angles of an n-sided polygon is the number of sides minus 2 times 180 degrees. So again, this fits the pattern for exactly those 3 things we did. So a triangle is 3 sides. That would be 3 minus 2 times 180, or really 1 times 180. A triangle has 180 degrees. 4 sides would be 4 minus 2 times 180, which is 2 times 180, exactly what we found. And then just for completeness, 5 sides is a pentagon. That's 5 minus 2 times 180. It is 3 triangles, exactly what we found over here. Okay? So this is the formula that we're going to use more generally. If I have a 30-sided figure, well, then the angles are going to have to add up to 28 times 180. So let's try an example utilizing this, and we'll work with a regular octagon, aka a stop sign. So a stop sign is the shape of a regular octagon. We're going to determine the measure of an interior angle. So interior means I'm trying to figure out what is one of these angles going to be for a regular octagon, okay? So that means all of these angles are exactly the same. I know my picture doesn't necessarily look like it's regular, but that's because I had to draw it by hand. So my goal is to figure out what does this angle measure out to be. But again, they are all exactly the same. So what I need to do is I need to figure out in total, what do these 8 angles add up to? So the total sum of the interior angles is, I've got an octagon, so that's 8 sides minus 2 times 180 degrees. So that's really 6 times 180. And if you go ahead and plug that in your calculator, it ends up being 1,080. So since it's regular, all 8 sides are exactly the same. So the value of x is I take that total and I divide it by however many angles there are. So every single one of these angles is going to be 135 degrees. Okay. Now that we know that, we're going to find the measure of exterior angle 1. And so just for reference, what that means, exterior angle is if you were to continue that side in a straight line, what is that value right here? So I know that this angle is 135 degrees and it forms a straight line. So the measure of angle 1 plus 135 degrees must be a straight line. So this will equal 180. So going through and solving, all I'm going to do is subtract 135 degrees. So the measure of my exterior angle 1 will be 45 degrees. Okay. So like I said, with rectangles or quadrilaterals, we can talk about some special names because we know rectangle is the #1 thing. You can see I want to say that too when I talk about a quadrilateral. But really there's quite a few special types. So we're going to go over what each of these looks like and also what actually classifies it as that. So we're ultimately going to have 5 special types of quadrilaterals. The first is a trapezoid. And so the distinction we make for a trapezoid is that 2 sides are going to be parallel. There's absolutely no distinction about the length of these, but 2 sides of my 4 will be parallel. And then we really just connect the dots. So this is an example of a trapezoid. Okay. When I make this even more distinct now, and I make both sides being parallel, this is going to constitute a parallelogram. The only way that can happen, though, for both of them to be parallel is if they are exactly the same length. So these 2 sides are parallel. So we use those little arrows to indicate that. And then these 2 sides are also going to run parallel. And so I'm going to use 2 of those arrow marks to indicate that. So parallelogram means both pairs of opposite sides are parallel. And again, the only way that can happen is if they're also equal in length. So really, these sides are equal to each other, and these sides are equal to each other. So both pairs are equal in length. So moving on to our next special one, this is my favorite word, it is a rhombus. Okay. So we'll talk about rectangles and squares for a second now, but if you think about that classification, there's that phrase, all squares are rectangles, but not all rectangles are square, because you need something extra. It's the same kind of connection between parallelograms and rhombuses. So all I need are these two sides to be equal in length and these two sides to be equal in length. But they absolutely do not all have to be the same size. A rhombus is going to be that special case where their opposite sides are parallel, but every single side is exactly the same length. So if you need to, you really can even exaggerate this further to see this distinction. Here is an example of a parallelogram. The sides opposite each other are parallel and equal in size, but definitely this side is longer than this one. So a rhombus is going to make it so all four sides are exactly the same. So it's kind of like a tilted square. Okay. So every single side is the same length. And the pairs opposite each other are parallel. So the definition we have for a rhombus is it's a parallelogram but all sides are equal in length. Now going on to our rectangle. A rectangle is actually also a parallelogram because the sides opposite each other are parallel. But there's a distinction about the angles now within these. So we know what our rectangle looks like. Let's see if my tool wants to actually work. It's been drawing circles. Oh, fantastic. It did. So a rectangle is very precise in that these are going to be sharp 90-degree angles. So these sides across from each other are parallel, and so are these two. Okay? And then likewise, these sides are equal in length. These sides are equal in length. So it fits the criteria for a parallelogram. But it also has the distinction that all interior angles are 90 degrees. Then, if we go on to a square, it's really a special case of a rhombus. So a square is also a parallelogram, but it's also a rectangle, and it's also a rhombus. It's got the characteristics of all of them. So you have 90-degree angles, you have both sides are parallel, but you also have every single side length is the same. So for our square, see if I can draw this nicely. That's a decent square. The sides across from each other are parallel. You have 90-degree angles. And every single side is exactly the same length. So its best criteria is it's a rhombus with this extra stipulation that the angles are 90 degrees. So a square is a rhombus, but all interior angles are 90 degrees. So hopefully you'll be good at identifying from the figure what type of classification it is. But really the bulk of what we want to do within this section is talk about perimeter and area. So first we're going to go over what each of those things are, and then we're going to go through all these different shapes and the formulas we have for each. So perimeter, which is denoted with a P, is the sum of the lengths of the sides of a figure. So just to use this one here, it's basically if I were to walk along this figure, what is the distance that I would walk? So because it ends up being just a distance, this should always be just units. So if all the sides are in feet, the perimeter is feet. The sides are in centimeters, the perimeter is centimeters. When we talk about area, which is denoted with an A, this is the measure of the region within the boundaries of the figure. So how much space the inside of that shape takes up. So because of that, area could be feet squared, inches squared, centimeters squared. If you think about painting a wall, you're talking about the square footage you need to cover. Flooring is always done in square footage. So this is always going to be in the form where you have units to the second power. Okay? In the next section, when we bump it up to volume, that's a three-dimensional thing, so that'll be units to the third. So we're gonna go over each of these shapes, the things you need from them, and how to figure out those different quantities. Perimeter is one of those things I never tell you to remember a formula for, except for the circle. Because with perimeter, it's just adding up the side lengths. The areas, however, are something you do need to know. So if I have a triangle, let's say the sides are A, B, and C. The perimeter is just directly adding those three sides together. To be able to find the area, though, I need a little bit more information. So what I actually need is a right angle somewhere within here. So if I have a right triangle, it's fantastic. However, you typically don't have a right triangle. So what you'll need is another key component that forms a right angle with one of the sides. So this is what we like to call the height. These two key pieces of information that form the right angle are what you use to find the area. So the area of a triangle is going to be 1/2 the base times the height. That's why I like to use B. Okay. The reason for that is hopefully you remember the area formula for a rectangle, length times width. Really, a triangle is half of that. So it's 1/2 the rectangle formula. And you need the two sides that form the right angle for that. So looking at our next shape, when we have a rectangle, again, you can call these A, B, whatever you want, but for a rectangle, remember these sides are the same, so I'll call those the length. These sides across from each other are the same, they're the width. The perimeter is you just add them all up. But really you have one W plus another. So we can condense this formula a little bit. It's 2 times the width and you have 2 times the length. And then the area of a rectangle is length times width. Okay. And again, that's where the triangle formula comes from because the length and the width form that 90-degree angle. And my triangle is half of that when I cut this down the middle. When we talk about a square, it's really not anything special, extra, because all of these sides are the same. So if I call these S, the same formulas still apply. It's just a little bit nicer because it's all the same. The perimeter is you have 4 sides with length S, so it's 4 times that. And the area is one side times the other, so S times S gives you S squared. Moving on to our trapezoid, I still have key pieces of information that I need to know. So if these two sides are parallel, they are not required to be the same length. So this top one, I'm going to call base 1, and this bottom, I'll call base 2. Same thing with the sides, they're not required to be the same length. So I'm going to call them S1 and S2 for side 1 and side 2. My perimeter, and this is why I don't like memorizing a formula, is I have to add all of these up. And there's no reason to remember that formula, just add the side lengths. Now when it comes to the area, it kind of deals with the area of a rectangle, which is length times width. The problem is you kind of have two different lengths here, or two different widths, whatever way you want to call it. And I don't have quite a 90-degree angle anywhere, so again, I'm going to need another piece of information. I need the distance between those two parallel sides. So you would think, okay, you take the height and you multiply it by the base. The problem is you've got two of them. So what you really are going to do is find the average of these. So the area is 1/2 base 1 plus base 2 times the height. Because again, just to kind of show you, you could rearrange this. Base 1 plus base 2 over 2 is the average of the bases, and then you times it by the height. But that formula just doesn't look as nice, which is why we write it as 1/2 the height times base 1 plus base 2. Okay. When it comes to a parallelogram, it's the same kind of idea here. The only difference is these sides are exactly the same, so I don't need to find the average of my bases. But I do still need to know that distance between them, what that height is. So in this case, this side is the base, because again, it's the same. And then these sides are also the same, so I'll call them S and S. So my perimeter ends up being, just adding them all together, you get 2B and 2 S's. And my area then is just going to be the base times the height. I don't need to average anything out. So same formula as a rectangle. Now the only other shape I'm going to add in here is not technically a polygon because it doesn't have sharp sides that form a vertex, but it is still an important shape for us. And that's going to be our circle. So a circle has a fixed point in the center, and then it's defined by all of these points around it being the same distance to the center. So no matter how you measured the distance to the center, it's the same. And that particular distance is super important to us. It is called the radius. And then in addition to that, if you look at 2 times the radius, so you go through the center, this would also be r. So this entire distance is 2r. That is really called our diameter. Okay. When I talk about perimeter, I don't like to use that same word because again, I don't have the sharp edges. So instead, this is called our circumference. But it is like the perimeter. Okay. The way we find the circumference is we take the number 2, we times it by pi, and then times it by the radius. Okay. But really, 2r is exactly the diameter, so another formula is really the diameter times pi. So we like to put pi out front. And just for clarity, pi is just a number. It's about 3.14159. When we go to find the area, it also deals with pi. And again, you need to get units squared. So the only way I can do that, because I only have one piece of information, is by taking the radius squared. Okay. So these are our different area formulas that you do need to know on your own. You will not be provided them. So we're just going to try really a ton of different examples where we're going to determine the area and the perimeter of the shape. And then also if we've got shaded regions, how do we figure that out? So we're going to start with an example that does exactly that. We're going to determine area and perimeter. So you can kind of take liberty to be able to identify the types of figures. So here we've got 2 sides given to us and 2 sides not. You can pretty much assume that this is going to be a parallelogram then. So these sides are the same. So really I can fill this in. This side is 300 centimeters and this side is 27 centimeters. Again, definitely not drawn to scale, but that's totally okay. So perimeter is the nicer of the two things. I just go ahead and add all of these sides together. So starting with 300 at the top, we do 300 plus 27. The bottom side is 300 and the last side is 27. So if we add all of these together, it ends up being 654. But again, I'm given units. These are all centimeters, and my perimeter is a one-dimensional distance, so the unit is just centimeters. Now moving on to the area, I need the two pieces that form that right angle. So that would be this distance here, which is the height, and the right angle it forms with is 300. So my area is the base times the height. The base is 300, my height is 20. So if I multiply these two, it gives me 6,000. And then my units should be square because they are an area. So that is centimeters squared. Okay. Moving on to the second example, this one is a circle. And they tell us this entire distance is 13 millimeters. But what I need is just this particular distance here, which is half of that. So my radius is going to be that 13 divided in half. So the radius is 6.5 millimeters. So again, to find perimeter, again, we call it circumference for a circle. That is 2 pi times the radius. So that's 2 pi times 6.5. And then depending on what the directions specifically state, I didn't do that here so I could show you both ways. Going ahead and multiplying the 2 and the 6.5 gives you 13 pi. And then the units are still, this is a perimeter-like thing, so it's one dimension. The exact value is 13 pi millimeters. If it tells you to round, that would tell you to plug in pi in your calculator. And so if you do that, you should see this is around 40.84 millimeters. So again, it just depends on what the instructions specifically tell you. If it says exact, leave it as is with the pi. If it doesn't say exact and tells you to round, then you plug in the value for pi. To do my area, same thing. My formula is pi r squared. So plugging in that my radius is 6.5. If I square that, the exact value is 42.25 pi millimeters squared. And then if you do 42.25 times pi, approximately this is 132.73 millimeters squared. Okay. So this is just two examples, but we're going to work with the other shapes in the next examples as well to try to figure them out. So we're going to determine the area of the shaded region. So this is going to require a bit more work because ultimately I have two different figures that are going on here. So if I try to look at these examples, if I identify this bigger figure, the larger outermost piece is going to be a trapezoid because I have those two sides that are parallel and they're completely different values. But what I need to do, if I find the area of the trapezoid, it gives me all of this area. I need to remove this piece here, which is a triangle. So if I want to find the area of the shaded region, I can think of this as the area of the trapezoid minus the area of the triangle. So once I find those two pieces, I just take the difference and there is my exact area. So I'm going to start with the area of the trapezoid. So going through my formula just to write it out to start, that's 1/2 the height times base 1 plus base 2. So from my image, I have to figure out what are each of these different things. So the two sides that are parallel are my bases. Doesn't really matter which one you call base 1 and base 2. This one's just more natural for me to write base 1, and this is base 2. So I have these two things. Now I need to figure out the height, which is the distance between them. So again, that forms that right angle. Well, really, that's actually given to me right down here because I have those two right angles. So this is actually my height. So I have the two things that I need. So the area of my trapezoid is 1/2. My height is 18. Base 1 is 9, and base 2 is 11. So I really just need to simplify this. You could plug it all into your calculator, but doing it piece by piece, 1/2 times 18 is 9, and then 9 plus 11 gives me 20. So if I do 9 times 20, that gives me 180. And then it's an area, so it should be my units squared, and everything here is measured in yards, so my unit is yards squared. So I've got the larger figure, and from that I need to remove this triangle. So we need to find the area of the triangle next. So that's going to be 1/2 the base times the height. So I have to figure out what those two different things are. And so if I look at my triangle, I need the two sides that form a right angle. So in this case, I have the 10 and I have the 18. So I'm going to go ahead and get rid of these because those were my variables for the trapezoid. But this is what I would call the height of the triangle, and this is what I would call the base of the triangle. So the two sides that form the right angle. So the area of my triangle is 1/2 times 18 times 10. And again, 1/2 times 18 gives me 9 times 10. The area of my triangle is 90, and my units are the same. It is yards squared. So from my trapezoid, I remove the triangle, and that gives me the area of my shaded region. So I take the larger shape and subtract the smaller. The larger area is 180. My smaller is 90. So it happens to work out that the area of the shaded region is exactly 90, and then the units are yards squared. Okay. So let's try one more of these, and then we'll stop there so this isn't a 50-minute long video, hopefully. But we're going to do another example where I have one shape and I've removed another. So I need to figure out the shaded region. So again, I start by determining what's the bigger shape. And in that case, this is going to be a circle. So to find the area of the shaded region, I need to find the area of the circle. And then I need to subtract the area of this shape, which in this case has sides 8 and 6. So it is going to be a rectangle since I have those 90-degree angles. So it's the area of the circle minus the area of the rectangle. And this one, I don't think it said in the directions, but I'm going to go ahead and just round it to 2 decimal places. So starting with the area of the circle, that's going to be pi times the radius squared. Well, they didn't give me the radius, but that's okay. I can figure that out from the picture. So the entire distance through the center of the circle is 10. That means the radius has to be 5 meters. So the area of my circle is going to be pi times 5 squared. 5 squared is 25. So the exact area would be 25 pi. But again, I'm going to round this to 2 decimal places. That is about 78.54. And it's an area, so my units are meters squared. Next up, I got to find the area of the rectangle. And thankfully, that's much easier. It's just the product of the 2 sides. So it is the length times the width. The length is 8, the width is 6, so the area is 48. And the units are the same, it is meters squared. So the area of my shaded region is then the circle, which is 78.54, minus the area of the rectangle, which is 48. And it's a rough estimate, because again, I didn't have the area exactly. If you're not good at putting the approximate or equal to sign, it's okay. This is about 30.54, and the units again are meters squared. So give these problems your best shot. Again, identify the bigger shape, the shape you've removed, break it down into things that you know how to work with much more easily than these hard figures. Because there's no way without intense trig would you be able to determine this section on its own. It would just be too complicated for you.